So here is where we left last time. So we spoke about solving equations of the form 2 to the power of x equal to 5. Let's see if you remember how such a what solution did we offer. Would anyone here type in the comments what's the solution to 2 to the x equal to 5, please? Okay, Stephen, and thank you, Hu. All right, so you see the question was, guys, let's see if you're waking up. 2 to the x equal to 5, what would you say x equals to? All right, then. Only 2 people remember? So the answer is log base 2 of 5. And this is nothing more than merely a label. It means place me on top of 2 and you will get 5. As in this Alice in Wonderland vial where it says drink and you will get small. It doesn't tell you what calculation is being done. It just says place me on top of the base number. So log, it's like some foreign language in place me over 2 and you get 5. In general, if it's a to the power of x equal to b, you would say the answer is log base a of b, to mean place it on top of a and you will get b. Let's have a quick comprehension check. Please, in your solution, type what is a, b, c, and d. Good, Stephen. Come on, guys, wake up. Okay. Good. Some of them you can write something nicer for, right? So there's most of them not, but one you can write something easier. That's good, Lakey. Thank you, Edwin. All right. So the solutions, as many of you have said, are for a, it's log base 10 of 3. Means, you see, just something that you place over 10 to get 3. That's what the solution is. The solution for b, log base 6 of 2. The solution for C is log base 5 of 7. The solution for D, it's log base 9 of 3, but we can guess the answer is 1/2 because take the root of 9 and you get 3. Good? So here again, guys, you see it should it should arise this type of worry that we are not really doing anything. We haven't solved anything because we just gave it a name. This x was just a letter. Now we gave it a very particular name. It only expresses several things, though. It expresses the idea, perhaps, that the solution is unique. So there is only one thing that you can place on top of, let's say, 10 to get a 3. Only one thing that you can place on top of 10 to get 3, and that there is something to be placed on top of 10 to be able to get 3. Yes? So we can discuss why would we believe that solution exists. So again, in your entire math career, you saw such situations happen again and again. You perhaps might have not noticed them. So for instance, when you solve the equation x squared minus 2 equals to 0, your solution would have been plus root 2 minus root 2. But if you think about root 2, it's just a notation, just like log-based 10 of 3 is a notation. You're simply giving it a name. So this is saying a number that when multiplied by itself will give you 2. So you did not really find the number in the sense it's not a 3, it's not 1/2, it's, you haven't found the number, you haven't, it's not what the calculator gives. And here is a very short comprehension check, guys. It's a bit difficult to answer in text, but let's see if anybody will speak or you do try to answer it by text. I want to see if you remember what is a notable difference between polynomials and functions like tangent, sine, e to the x, log, root, etc. Why polynomials? What's so special about polynomials? Perhaps you can also say rational functions. So polynomials and rational functions are of that type, but especially polynomials. And other functions are not necessarily right away of that type. Do you understand my question? So why fundamentally polynomials are more familiar than tangent, sine, e to the x, etc.? No worries, Gabriel. No worries at all. Right, so I asked you this question to see if you can figure it out. What's so special about polynomials as opposed to tangent, sine, e to the x? Something that we discussed again and again. I would like to hear from you. Yes, Dragon, from all the lectures should be on my website, if I am not mistaken. Not on the website, my apologies. The lectures are on YouTube. Just type, this is the morning section, so you can type Arkady Etkin, Calculus M, or something like that, right? You can find it on my website. On the website, I apologize again, on YouTube. I didn't link anything to the website. All right, so I see nobody volunteers anything today. That's too bad, guys. I mean, look at this polynomial. What happens here is I can clearly see its digestion process. So the input is squared, and then you subtract 5 times the input and add 1. So you can see the digestion process. Whereas sine, e to the x, log, and root are just names. It doesn't tell you how the process is working. So for instance, some people simplify the x out of the parentheses. So sine of x squared over x, they will write sine x. And that is very wrong. It is, and this mistake, it's hard to say why people make this mistake. Maybe there is no meaning whatsoever. It's just, I imagine they see parentheses, they think there is multiplication and division. There is no, this is just what? This means there is no sine multiplied by x squared. It is some name of a function, and it has eaten x squared, and I have no idea how x squared is digested, what will become of it. There is no reason I can cancel x. You with me? Sine of x is not sine times x. This is meaningless. This means a known function that we understood something about has digested x, and I'm not sure what the output looks like. I do know what it means when you simplify. The output looks exactly like what it looks like after you have eaten your meal. We did learn how to expand e to the x and represent it as an infinite polynomial, and we asked what would be the situation for sine x and cosine x. Can you find an infinite polynomial representation for sine and cosine? And of course, now we would be interested in knowing, can we find similar representation for logarithms? So here is a comprehension check, guys. We begin with properties. So what is 5 to the power of log base 5 of smiley face? Five to the power of log base 5 of smiley face. Muhammad says 1, interesting. Guys, a very simple comprehension check if you understand what is a logarithm. Edwin says 5. I'm asking you to read this expression. What does log base a of x mean? And what should be, do you understand the instructions? Okay. Basic instruction, guys. What is log base a of x? Does the expression mean anything? Look at it. The instructions are right on top. Place me over a and get x. So what do you get? Exactly. Smiley face. If of course the expression makes sense, guys. It's just basically following the prescription. If you place this thing on top of A, you will get whatever you have here. So if you place this thing on top of 5, which is done, you should get the smiley face. Understood? Of course, you have to be very careful. What is 5 to the power of log base 5 of minus 7? So, okay, Edwin, thank you. Thank you, Stephen. Okay, we have 2 people, 3, 4, 5, and then once a few people wrote it, others become confident. First of all, guys, there is nothing wrong about, well, there's nothing terrible if you are mistaken. Big deal. The thing is, exactly. Can it be minus 7 though? So here you gave a name to something that does not exist, you see? So you did express a philosophical belief that there will be something. It says place me over 5 and get minus 7. But if this is supposed to be a real number, you know that if you place any positive number on top of 5, you will get a positive number. If you place 0, you will get 1. If you get a negative number on top of 5, you also get a positive result. So there is no way to obtain minus 7 from real numbers. Yes? We don't even know, maybe you do, but at least we haven't really discussed existence. How do we know that it can be done? So it's undefined, at least for real numbers. Okay? But we will, so you have to be careful that even when you give something a name, it might be that you give a name to nothing. So here are some logarithmic properties, right? So you see, even though we don't exactly know what logarithms do, how they work, we can see that they should have the following properties. For instance, log of a that produces m times n, it's the same as log of am plus log of an. And here is the reasoning for it, guys. Are you ready? So let's, I'll show you how to do one, and you will try maybe to do a few others. So proof, right? So all I know about this expression is if I place it over a, I get m times n. So that's what I do. There's not much I can do with those expressions. I place it over a, and I get m times n. Are you with me? But what is m? How can I get m out of a? I can write m as a log base am, and n I can write as a log base an. And when I multiply 2 expressions that have the same base, I can add the powers. So I get a to the power of log base am plus log base an. And because the answer is supposed to be unique, they must be the same. You see, this and that are the same. Good? Did you understand the explanation, guys? Please write Y or yes or something like this so that I know that you are here. Would anybody care to write the explanation? Maybe you can write the explanation for Tuden. Yes, let's go again through it. guys, you see, you're just dealing with you see this object. All you know about it is that if you place it on top of a, you get what's inside of the logarithm, right? This means place me over a and you get m multiplied by n. So that's all I know about this. So I place it over over a, and what do I get? I get m multiplied by n. Clearly, that's true. Then I can put them in red and blue boxes. What's in the red box, m, can also be written as a to the power of log base a m. You all agree? How do I get m as some power of a? I just take a and raise it to the power of log base a m by those instructions. And I do the same for n. We have a to the log base a of n. Now, when I multiply one number to some power to the same number to another power, I add the powers. So I then see that what I see over a is it must be equal to what I see over this a because of the assumption on uniqueness. For that, you, by the way, use the intermediate value theorem. You see, how do you know the existence of logarithms? You might begin discussing the existence of logarithms for the exponential function, which we know is continuous. So the exponential function, you know, e to the x. E to the x looks like this. Okay, and we know it covers all positive numbers. It's differentiable, e to the x, so that is y equal to e to the x. It's differentiable, and the derivative is the same as this function e to the x, which means because e to the x is always positive, it means that we always have positive slope, which means the function is increasing, which means that by the intermediate value theorem, you say increasing to infinity. So if I say, if I take number, here is 1, here is 2, here is 3, between those values, by the intermediate value theorem, I can take every other given value. So for instance, there will be a solution here. So that solution is log. So that solution here it should be right. It should be, if this is y, that would be log base e of y. It will exist by the intermediate value theorem. So that's just a little over why do we know that we have solutions to it and that they are unique for real numbers. Now I would like you guys to see if you can establish the law number 2, that logarithm of a m divided by n is logarithm am minus logarithm an. Yes, so you can type something like this, right? You can say, for instance, a to the power of log base a. You can even say log a of m over n equal to, you see, you can figure out a way to write it if you want. Okay, I want you to prove number 2. You said you understood 1, so show me that you can prove property 2. Lakey, great. You're I see that you see the idea. Very good, guys. Well that right. Yes. So establish this. So you see the property written. I just want to see if you can justify it. Like, give me a short proof in the text. So yes. So give me a short proof in the text. Good. Good. All right, guys. Let's do that. Here we go. Okay. So 2, I actually didn't write it out. It's a similar calculation. Let me, I guess, write it here. So I want to understand what is what I just take a to the power of log base a of m divided by n, and that's simply m divided by n. Yes, which can be written as what? So this can be written as a to the power of log base a of m. That's the numerator. A log base a of n, denominator. And when I have a to one power divided by a to another power, that's a to the power of log base a of m minus log base a of n. How many of you thought this way? Write in the comments. Yes, good, Edwin, right? Good. Yep. Yeah, it's kind of uncomfortable to write in text, but you see what I mean. Good. If at some point I can also give you a shared board, you can write it on it, I suppose, right? Definitely in office hours, that's easy to do. All right. And then we have other properties. Then we have property 3 is that I can drop the power below the logarithm. You see, I can drop it down. How do I know I can do that? Well, I do the same procedure. A to the log base a mr, it's mr. And what is m? I just represent it as log base a log a m to the power of r. And then I see it's just a property of exponents, right? I just multiply this by that and I get this expression and I'm done. You see that? So they must be the same. Now you have property 4, it's called change of basis. In other words, the idea is that I can represent every logarithm whatsoever using just one logarithm, right? I can pick the logarithm I like and represent all the others in terms of it. Okay, so suppose, for example, that we like log base e, but we're given log base 2. How do I convert it? Okay, you understand what I'm asking, guys? So there is something special about e to the x, and we do know, I'm not sure if you understood my very quick explanation. It's easy to see using calculus, using the intermediate value theorem, for instance, that the idea of logarithms, that it's unique, and it's possible to find a logarithm for every positive number. So that is true for e to the x. So how would I figure out what is log base 2 of 5 in terms of log base e, right? So what I can do is I can think of this as I can do this. I can say, oh, okay, this thing is equal to 5, yes? But what I can also figure out that that 2 is equal to e log base e of 2. Yes, and 5 is equal to e log base e of 5. So I can do that. And what I can do with this information, I see that e to the power of log base e of 2 raised to the power of log base 2 of 5 will be e to the log base e of 5. And so I have then this equation. I have that e log base 2 of 5 times log base e of 2. I just use multiplication. You see, it's like it's e to one power raised to another power. I multiply powers is equal to, say, e log e of 5. So the powers are the same. So this is the same as that. Good? Understood? And so I can now solve this equation. I say that log base 2 of 5 is equal to log base e of 5 divided by log base e of 2. You understood my explanation so far? So I can calculate logarithm if logarithm base 2 of 5 can be calculated as a ratio of 2 logarithms base e. So I can always change from one basis to another. That's what I'm saying. Do you understand? Confirm if you do. Morning Christian. Yes. Goal. So help me explain it again, guys. What is the goal? Is imagine that you want to convert one logarithm into another logarithm. One reason for it is, for instance, logarithm base e are much better understood than other logarithms so far, because we know that e to the x is differentiable. We spend all this time, we developed it, it's differentiable. We know that the derivative of e to the x is e to the x, which means e to the x is continuous, and I can use that information to infer that logarithms base e exist for all positive numbers. It's possible to calculate log base. Let me try to say that this way. I can calculate log base e of any number of 7. How do I know I can calculate it? Because the question is, to what power must e be raised by to get 7? Yes, that's what this is saying. And it says the power is unique. So now e to the x, I know what it would how it would behave. Its derivative is the same as the function. So I'm wondering where we will have 7. So I know that the easiest places to find e to the x is for so what power will give me something bigger than 7? That's that's pretty quick. So for instance, if I have 1, 2, 3, so e to the 7 will be somewhere between 2 and 3. So if I take 2, I'm here, and I am so it's e squared. E squared, I am below 7. If I take e cubed, I am above 7. So because the function is differentiable, it is continuous, and therefore by the intermediate value theorem, the 7 is somewhere over here, there will be a solution. This is the solution. All right, this is the power. This is the power to which e must be raised by to get 7, and that's log base e of 7. Before I continue, guys, do you understand what I just said? Yes, are you sure? So that's where the intermediate value theorem is truly useful. Think about it, guys. If you have a very good understanding of how we develop the derivative of e to the x, we can calculate it. We have all sorts of means, right? We know that I know how to calculate things, right? So I know, for example, what is e to the power of 3. E to the power of 3, it's simply 1 plus 3 plus 1 half 3 squared plus 1/6 3 cubed and onwards, right? So I can estimate e cubed. I can estimate for any number you give me, I can estimate what e to that power will be equal to. Because the function is continuous, and because the derivative of this function is everywhere positive, it means slope is always positive. Slope is positive. Means the function is increasing, which means that there will be, if there is a solution, it's unique. See, it never returns to 7. Once it passes 7, it never comes back. So there will not be two solutions. There will be only one solution. Good. And what more is, because the function, the limit of e to the x as x goes to minus infinity is 0. And if you go in the right, it will be plus infinity. So we know that e to the x stretches and covers all the positive y-axis. So it's possible to find solution for every positive number. By the intermediate value theorem, therefore I know that if I plug 2 into e into the x, e squared is going to be too small. I will not get 7. If I plug 3, it is too large. I get something more than 7. By the intermediate value theorem, there will be a value between 2 and 3 that solves this equation. So log base e of 7 exists. I know it exists. Good. So I do not much know about other logarithms because I haven't perhaps found their derivative, or maybe in my calculator it's not so much true now, but I do not have this particular bottom. So let's say I want to calculate log base 205. I can convert log base 205 into an expression involving only e, and that's what I did over here. So how did I convert it? I see that log base 205, if I place it over 2, I get 5. Now I can represent 5 as log base e of 5, and 2 I can represent as log base e of 2. And I have this equation, e to the log base e of 2 times to the power of log base 2 of 5. Multiply it out, you get this expression. You get log base 2 of 5, log base 2 of e, equal to log base e of 5. And so solving this equation, just red equal to red. Log base 2 of 5 is going to be log base e of 5 divided by log base e of 2. That's the change of basis formula. In general, I can convert from one base to another. So here is how I convert it. It's the same idea, converting from one base to another. So before one thing, guys, first question. Did you understand why I might consider changing bases? The idea here is that I can describe every logarithm in terms of any other logarithm. Give me a logarithm, I can convert its description and use calculations only in terms of another logarithm. And there is one logarithm, again, that is particularly that I particularly know about. And that's the logarithm base e. Because I have dealt with e to the x, I know how to differentiate it precisely. If you remember how to take the derivative of e to the x, in the other derivatives, we only approximated what's the derivative of a to the x at 0. But e to the x has derivative at 0 equal to 1. So I know the derivative of e to the x exactly. Are you with me, guys? I do not see your faces and I see no comments, so I tend to imagine that you are sleeping. This is what you call precalculus. Good? So here is property 4. B to the power of log base B of m is simply m, right? And then what I can do, I want to basically write log base B of m in terms of base A logarithms in general. So that would be, all I do is I convert B. B is A log base A of B times this logarithm. Now, A to 1 power multiplied by another power is just A product of the powers. Yes? And that would equal, it's the same thing here. So it must equal to m. And that is equal to A log base A of m. So then I look at the green line must equal to this green line. So log base AB log base BM equals to log base AM. And then I just simply divide. I want to solve this guy. So I simply divide log base AM by log base AB. And that's what it is. So for instance, here is what I just derived, guys, if you still don't see it. For instance, suppose that I want to write log base, let's see, well, log base 2 of 3 in terms of log base 10. So that would be, in terms of log base 10, it would be log base 10 of 3 divided by log base 10 of 2. Those expressions are the same. That's what I just verified. Let's see if I can give you a quick question, comprehension check. Okay, so let's see. So tell me, please, what is log base 3 of 5 in terms of log base E? Okay, evaluate it in terms of log base E. What do you type in the comments quickly? Yes. Yes, Lisha, yes. Yes. Come on, faster, guys. So we yes. Yes, so all you do is simply, according to this formula, you write log base E of 5 divided by log base E of 3. That's the conversion. Good. So now let's return back to the problem of finding derivatives of exponential functions. Remember what we did when we started. We took the derivative of 2 to the x, and what did we write? We wrote something like 2 to the x plus h minus 2 to the x divided by h. We factored out the 2 to the x, and we found that this limit is approximately, let's say, 0.69, whatever it is, right? But now we can actually find the derivative precisely what it is. Good. What is it precisely? So the derivative of 2 to the x, it's the derivative of e to the ln, by the way, guys. Ln is the base e natural logarithm. It has a special name. Instead of writing log base e, you write ln. Okay, clear? So that would be the same as e to the power of ln to x. And then because I can drop the powers, it is the same as the derivative of e ln of 2 times x. So what happens is that when I take the derivative, it's e to the whatever power multiplied by the derivative of ln of 2 times x. The derivative here is simply ln2. So you convert it back. What is e to the ln2x? It's just 2 to the x. So the answer is this 0.692. Exactly, it is ln of 2. It is the base of the natural logarithm at 2. Are you following me? So before we gave it an approximation, but now we know for sure, because we know the derivative of e to the x. That's what we developed. We now actually know that this number that appears here is the natural logarithm of 2. And in general, if I take the derivative of a to the x, I'm actually taking the derivative of e to the power of x ln a. And the derivative here will be e lx ln a times ln a. Ex ln a just can be converted back to a to the x, and then we have ln a. So the limit as h goes to 0 of ah minus 1 over h is logarithm of base e of 2. That's what we found. All right, guys, here are some examples, just quick calculations. Find those derivatives, please. Find a, b, c, and d, and do it fast. Thank you, Kirill. Good. You understood, guys. If I take the derivative of e to the x, I get e to the x. But if I take the derivative of 5 to the x, it's 5 to the x multiplied by ln 5. Come on, guys. You can do it. Good. Good, Lisha. Only 2 people so far. Okay, Zainab, great. Great. Okay, Sumaya, good. Good, Stephen. Okay, Zakia, good. All right, guys, I'm gonna begin solving. I need to move. So the derivative in A, it's 5 to some power. Derivative of 5 to some power is 5 to the same power multiplied by a logarithm base e of 5, ln 5. Then the derivative of secant is secant tangent. So this is the expression. Now, for problem B, the main operation is product law. So we have this multiplied by x cubed. So first, taking the derivative of first function, it's 2 to the x squared times ln of 2 times the derivative of x squared, which is 2x, times x cubed, plus I don't bother the first function multiplied by the derivative of x cubed, which is 3x squared. Good? Simple enough. What's the derivative of c? Derivative of secant is secant tangent. So it would be, well, actually, let me wait. Quickly, guys, can you write c? Tell me what is c. So the full expression, Lisha, right? C, I want to see what is the full expression. Yes, Kirill. Good. Okay. Good, Sumaya. Through A? Yes, I'll show the steps, sure. All right, so I was asked to show the steps through A, guys. It was the derivative of 5 secant x, I believe. So what I get is it's 5 to the x that has eaten some trigonometric function. It's an octopus that has eaten a medusa. So what do I get? I get derivative of 5 to something is 5 to that something multiplied by ln 5 multiplied by the derivative of the something. Good? That's how I think. So, so derivative of outer function is 5 to the something times ln of 5. Did you get how I got this ln of 5, guys? Very don't you see, it's very easy to remember when if you happen to forget. So what happens then, it's really 5 secant x multiplied by ln 5 multiplied by derivative of secant is secant x tangent x. Good. And how do I know that the derivative of 5 to the x is this expression? Derivative of 5 to the x is the same as the derivative of e to the ln of 5 to the x, yes? And what is that? That's the same as derivative of ex ln 5, which would have been ex ln 5 times ln 5, because this is just x multiplied by a constant number. And when you take derivative of a constant times x, you just get the constant. Good? And ex ln 5 is 5 to the x. So I know that this is the general derivative form. You with me? So the next thing that we were doing is, I believe it was, what was it then? It was secant of 5 to the x. So now the Medusa ate the octopus. So what's the derivative of secant of 5 to the x? Well, derivative of secant is secant tangent. So I first have secant 5x tangent of what's in its belly, 5x. Now I need to multiply by the derivative of the inner function. Derivative of 5 to the x is simply 5x ln 5. Clear? Confirm if you understood, guys. So if you understood, do this last problem. It's a bit ugly. Do it fast, guys. I want to move on. Derivative of tangent 3 to the x plus 3 to the tangent x. Please do it very fast. Okay, Lisha, good. Very good. Come on, guys. It's not so difficult. It's just calculation. All right, Steven. Let's see. Looks good. All right. Still only few people answered it. I want to move on. Here it is. Derivative of tangent is secant squared. Plug in the inside. The inner function is 3x. Then the derivative will be 3x ln 3 plus derivative of 3 to some power. It's 3 to the power times ln 3 times the derivative of the power times secant squared. We're done. Tangent to the 3x, here it is. I take the derivative of it here. It's after the plus. Derivative of 3 to the tangent x, it's 3 tangent x ln 3 times the derivative of tangent, which is secant squared. Clear? So those questions, especially guys, if you stay after class, I can always give you lots of practice problems. All right, let's go to the next lecture. Oh, implicit differentiation. All right, guys.